Hi everyone, my name is Emilio Martinez-Pañeda and I am an associate professor at the University of Oxford. A few weeks ago, I had the pleasure to give one of the plenary talks of the European Corrosion Congress, EUROCORR 2024, and a number of people approached me and asked me if I could send the slides or record the lecture, so this is what I'm doing here. And as you can see, my goal during that plenary was to present our efforts in developing a virtual corrosion lab. Because being able to reliably predict corrosion in computers quickly and cheaply would be a game changer. Virtual testing has saved billions to the automotive and aeronautical industries, so it would be great to extend that success to corrosive environments. However, a good friend once told me, "Give up, Emilio, you're wasting your time. Localized corrosion is too complicated to be simulated with computers." And he may be right, but the point that I will try to make today is that thanks to two recent methodological developments in the computational sciences, we are now capable of developing the first class of mechanistic, physically based models that can reliably predict corrosion failures. The motivation for the work is clear. You all know the importance of corrosion, and hopefully politicians and funding agencies too. But the point that I want to emphasize is this one here. Despite decades of corrosion research, we're still unable to predict corrosion failures, which often have catastrophic consequences. These failures occur with increasing frequency and everywhere, in countries with very rigorous standards and safety factors. We have learned a lot about corrosion through excellent experimental research, but we have not been able to bring the physical insight into a model that can tell us when these things are going to happen. And the closure of half of France's nuclear power plants 2 summers ago due to corrosion damages is also a good example of this lack of predictive abilities. There are several reasons for this. Corrosion is a very complicated problem, as my friend said, but another important reason is that it's often difficult to test in our lab over the timescales and conditions of corrosion failures. You can see this sketch in this plot, where the y-axis is the time to failure, and the x-axis is a measure of the severity of the environment. It could be corrosion current density, for example. And a typical example of this is the corrosion of reinforced concrete structures. We run accelerated impressed corrosion current tests, but our goal is to predict failures that occur over decades, as the case of the Morandi Bridge a few years ago. So interpolating between data is easy, but going from here to here is quite a challenge. Of course, you can always feed the data in an empirical way with some fitting coefficients, but this is not going to be useful beyond your regime of calibration. And this is often done in various corrosion disciplines because, it's better than nothing. But if you want to go from here to here, you need a model that encapsulates the physics of the problem. A good simple example is Faraday's law for uniform corrosion. It allows us to extrapolate what will be the change in mass for a given time t as a function of physical parameters such as atomic mass, Faraday's constant, and so on and so on. And this is why uniform corrosion is well understood. But of course, uniform corrosion is not responsible for this catastrophic failure. So the goal here is to develop physically based models for more complex corrosion phenomena. We won't have the luxury of coming up with simple analytical expressions, but computers can help us solve the differential equations that describe the key physical processes describing localized corrosion. So the main takeaway and philosophy here is that we want to be predictive, and if we want to be predictive, we need to move away from big assumptions and fitting parameters. We need to explicitly resolve the physical processes taking place. We need models that rely purely on physical parameters. This is, of course, not easy to do, as localized corrosion can be a very nasty business with many physical ingredients. In a typical stress corrosion cracking scenario, you have a metal containing a defect that is exposed to an electrolyte, or you have multiple ionic species that are moving around due to diffusion, fluid flow, electromigration. In the interface between the metal and the electrolyte, you have chemical reactions, which might include material dissolution, the formation of a passive layer, the absorption of the deleterious species, such as hydrogen. Then these hydrogen atoms move within the metal, which is deforming elastoplastically due to mechanical loading, which is also rupturing the repassivation layer, and so on and so on. So there are a lot of things happening, all of them important, and all of them strongly coupled. The good news is that we know what are the differential equations that describe each of these physical phenomena, and that we finally have enough computer muscle and multi-physics finite element tools to solve them. So in a way, we can take advantage of the growth of computers and resolve the problem by brute force, explicitly resolving each of the physical processes involved. And this delivers a model that is physically based and relies only on physical parameters. You can see it here, for example, the Nernst-Planck equation. The parameters involved are Faraday's constant, temperature, diffusivity. Solving models with 10, 15 degrees of freedom per node was unthinkable when I started my PhD 10 years ago, but it's very doable now. And I won't get into the details of the computations for the sake of time, but there's significant work going on in the computational mechanics community to accelerate these calculations, both from applications going from batteries to corrosion. For example, in our group, we have shown that using LAMP integration schemes, we can accelerate by a factor of 1,000 some of these calculations relative to COMSOL, which is the typical commercial finite element package for this type of multiphysics simulations. Okay, so all of this is good news. Computers are big enough that we can resolve the physical phenomena as they happen in reality, but there's another challenge. In corrosion, defects are not stationary. The interface between the electrolyte and the metal is continuously evolving. You get pitting, a pitch to crack transition, so you need to capture this. And this is going to be closely linked to everything that I showed you in the previous slide. You can see it very nicely here with this example of corrosion fatigue in offshore wind turbines. And corrosion fatigue is what governs the lifetime of these offshore wind turbines, which is only 25 years. So you get an evolution of the pits, then those pits growing, and then eventually this kind of pitch to crack transition and the propagation of fatigue cracks. And everything is strongly coupled. The corrosion fronts evolves driven by local chemistry and mechanics, and the local chemistry and mechanics are themselves dependent on the corrosion front morphology. The stresses are larger, ahead of sharper pits, and the pH drops in occluded electrochemistries, as you can see here. So this is the second big challenge, holding back basically the development of physical models. You need to simulate the evolution of this interface, the corrosion front, and tracking the evolution of an evolving interface is a well-known mathematical and computational challenge. So let me show you this. If we think of the simplest way to mathematically express corrosion, we could define a normalized concentration of metal ions, which is equal to 1 in the metal and 0 far away from the corrosion front deep into the electrolyte. Then under conditions of activation control corrosion, the evolution of the interface velocity is given by Faraday's second law, and the concentration of metal ions in the interface is given by the Rankine-Hoogenberg condition. And when the concentration of metal ions reaches the saturation value, then instead you have diffusion control corrosion, so that the concentration of metal ions is given by this Dirichlet boundary condition, and the interface velocity is given by sampling the saturated concentration on the Rankine-Hoogenberg condition. So you have to impose on the moving corrosion front boundary conditions of various types, Robin, Dirichlet, that are varying in space and time. This is simply a computational nightmare, and the reason why computational mechanicians have not been able to deliver models to predict the evolution of the corrosion. However, the good news is that a new technique has been recently developed that enables tackling interfacial problems of arbitrary complexity. These are the so-called phase field models. The idea is quite simple. Instead of describing the interface between two phases, such as aqueous electrolyte and metal, as sharp and discontinuous, you can smear that interface over a finite domain and use an auxiliary variable, the phase field, to describe where the interface lies. And then you just need to define a differential equation for the evolution of this phase field. And this implicit method of describing interfaces is computationally very powerful, and I'm listing here some of the key advantages. Essentially, you don't have to define those nasty moving boundary conditions. You can capture topological changes, such as the coalescence of multiple bits in a natural way, and the method is ideal for coupled multiphysics problems. In fact, phase field modeling has been a revolution in many areas of science and engineering. It all started in the condensed matter physics community, what is now by far the most widely used technique to simulate solidification and macrostructural evolution. It has also very quickly become the dominant technique to simulate fractures, and you can see here why. Very complex cracking phenomena can be captured. This is the output of a simulation. You can see here crack branching, coalescence, nucleation of secondary cracks. And we and other groups in the US and Asia have recently shown that this paradigm can also be extended to corrosion. The phase field can be used to describe the evolution of the electrolyte metal interface, the corrosion front. So the phase field is going to act as a marker, and it's going to tell us where the corrosion front is, basically by taking a value of 0 in the electrolyte and a value of 1 inside of the metal. And throughout my talk, I will use blue color to denote electrolyte and red color to denote metal. I'm going to skip all the mathematical details for the sake of time, but if anyone is interested, this is all derived from a free energy functional, so all is based on thermodynamics, and the constitutive choices are based on the so-called KKS, Kim-Suzuki model, which assumes thermodynamic equilibrium between the phases. But basically, at the end of the day, what you end up with is two equations. One for the short-range interactions, that is corrosion, material dissolution, which is what you see here. And this is basically the phase field equation, an Allen-Kahn type of equation. And then a second equation to describe the transport of the metal ions, which is a diffusion type equation. I will not give details on the numerical implementation, but it is straightforward in any finite element code. And we openly share all our code so you can see it all there. The key thing that I want to emphasize is that the upper equation is governed by this mobility parameter L, and the bottom equation is governed by this diffusion coefficient D, and both have a clear physical meaning. The diffusion coefficient is obvious, and as you can see here, the mobility coefficient, you can easily demonstrate that it's proportional to the corrosion current density. So it's straightforward to quantify this value of L from a simple uniform corrosion experiment. So let me show you how this works with the simplest example, the pencil electrode test, which is effectively 1D corrosion, as you have uniform corrosion of this metallic bar. You can see here some representative results. On the left, the evolution of the corrosion front, as described by the phase field, and on the right, the evolution of the concentration of metal ions in the electrolyte. And the good thing is that for this 1D problem and conditions of diffusion control corrosion, there's an analytical solution, so we can confirm that the model is giving us the right outputs, as you can see here. But also important, we want to show that the model can capture naturally the transition from activation control corrosion to diffusion control corrosion. You can see here on the left that if we ramp up the corrosion current density through this L parameter, the mobility coefficient, we go from the linear behavior of activation control corrosion to the parabolic behavior of diffusion control corrosion. And of course, when we are in the diffusion control corrosion regime, then the peak depth is going to be very sensitive to our choice of diffusion coefficient. So there's another key takeaway. You don't have to worry about going from activation to diffusion control corrosion, adding some sort of, I would say, criteria that you need to change in time and space, because the model can naturally capture this. But of course, we're not interested in simulating 1D problems, uniform corrosion. Our aim is to capture corrosion problems of arbitrary complexity. We want to simulate 2D and 3D problems. We want to capture peak interactions. We want to predict the role of secondary phases, intergranular corrosions, and so on and so on. And as you can see here, this is one of the core strengths of this method. We're capable of doing all these things, and this allows us to bring complementary insight to the experiments that we do in our labs, and also rationalize a number of observed phenomena, including some interesting synchrotron pit growth observations reported some years ago, as you can see here on the right of the slide. But even more important than these computational capabilities is the ability to resolve the underlying physics. As I said at the beginning, my friend claims that corrosion is too complex to be simulated with computers, and he might be right. There's many things happening and all playing a role and all coupled. But all of that physical phenomena can be simulated in a computer nowadays. We can incorporate the role of electrochemistry, the role of microstructural anisotropy, the interplay with hydrogen ingress and embrittlement mechanisms, the coupling with mechanical fields, which can disrupt the passivation film and enhance also corrosion kinetics, and the electric double layer and the production of the formation of corrosion products, and others. These are some of the avenues explored by our group, but what excites me about this emerging field is that there's so many possibilities that are ready to be explored. Corrosion is indeed a complicated problem, a very rich and complicated problem, but we can finally incorporate all that richness, all that complexity into our models. So I'm just going to finish my talk with some examples of these applications. As a mechanician, the first ingredient that I was keen to add was the role of mechanics. And mechanics can impact corrosion in two ways. One is by enhancing corrosion kinetics, as nicely described by Goodman. As you can see here, the corrosion current density is enhanced by plastic straining and also by the hydrostatic stress. And we can easily incorporate this into our model because the mobility coefficient, the L parameter, is proportional to the corrosion current density. So we solve the mechanical problem, as you do in any regular finite element code, and bring that information, those hydrostatic stresses and plastic strains, into L, which is no longer a constant. And we will test the outputs of this model by comparing against searing experiments where you apply a constant load and measure, the degree of corrosion. Here you can see the results. As you can see, the model delivers an excellent agreement with experiments over 2 levels of applied load for both the degree of corrosion, but also for the morphology of the corrosion defect. You can see it here. These 2 figures have the same scale, and there are multiple pits here. We choose to model only the main pit. We could have modeled multiple pits, and you can see that there's a relatively good agreement. The other way in which mechanics typically impacts corrosion is by disrupting the passive layer, of course. And as you know, this is a cyclic process. You form a passive layer, which is becoming more stable with time. So then you reduce the corrosion potency. But then when your strains are large enough, then you fracture the passivation layer, and that leads to a sharp increase in corrosion current density. And again, this is straightforward to incorporate into our model because we are solving a mechanical problem. So we know when the strains are large enough to cause film rupture. And exploiting the relationship between this mobility coefficient and the corrosion current density, we can again enrich the definition of this L coefficient to incorporate this film rupture dissolution repassivation mechanism. And then when you do that, basically you can run simulations that resolve the interplay between the straining kinetics and repassivation kinetics. And among other things, you are able to predict naturally the peak to crack transition, which is something that the community has been trying to do for decades. Another important physical ingredient is the role of microstructure. We know that not only we have an anisotropy in the mechanical behavior due to the anisotropy of the crystal properties, but also corrosion rates are sensitive to the crystallographic anisotropy. So we take experimental data for different crystal orientations and define grain orientation dependent potential. And then there's many things that you can do with this microstructural enriched model. For example, you could combine it with EBSD images to look at real microstructures. In our case, what we did is to learn these things that you see here. One is to map the regimes where microstructure matters. When do you need a full microstructure analysis? So here you can see the type of results we can get. You can build this type of maps where you have grain size on the vertical axis and over potential on the x-axis, and then we can quantify under which conditions you can get away with a simpler model and under which conditions you need to resolve the role of the microstructure. We can also learn about the interplay between corrosion and isotropy, mechanical anisotropy, and grain size effects. And we have also shed light into the different corrosion susceptibility of additively manufactured alloys. Another key ingredient is electrochemistry. We can fully resolve the electrochemical behavior of the electrolyte and capture how it impacts corrosion through changes in conductivity. And you can see here that the model is getting bigger, but again, computers nowadays can handle this. And all the new physics that is being incorporated into this model relies purely on physical parameters. There are no mysterious fitting coefficients nor any strong assumptions. All the mesoscale physics is being resolved. And when you do that, then you can capture the role of solvent concentration, of applied potential, and you can see how the electrochemistry of the electrolyte evolves in time with changes in the corrosion front. And one of the last applications that I want to discuss, and this is one of my favorites, is what I like to call biocorrosion. predicting the corrosion of biodegradable materials in body fluid. There's significant interest in using magnesium for implants, and in this way, you have a non-permanent implant, and that will degrade as the bone or tissue heals, as you can see here. However, the issue with magnesium is that it corrodes too fast in body fluid, so people are trying different solutions such as alloying or composites. And this is a slow experimental trial and error process, so we have extended our models to handle this application with the hope we can accelerate the discovery of suitable biodegradable implants. And as you can see, we get a good agreement with experiments. And importantly, we can simulate the behavior of implants and stents in vivo as they were in the human body. We cannot do experiments in humans, so the ability of models to go from in vitro benchmarking to in vivo predictions is an important. We've also combined this type of phase models with phase. Oh, let me say one thing first. All the simulations that I showed you so far, as we typically do in our lab, and as you do if you do finite elements simulations in commercial codes like COMSOL, assume that you are imposing an applied potential. However, under natural corrosion conditions, you don't have such a condition, right? You don't have any applied potential in your metal. But we can develop models where the metal potential is a degree of freedom, is an output of the model, where we don't expose any constraints, and we can simulate corrosion under natural charge conservation conditions. And this is what you see here. So you basically can define this charge conservation condition here. And then we have tried to use these techniques, particularly to focus in collaboration with Carmen Andrade, to focus on understanding corrosion in reinforced concrete structures, to try to map the conditions, and understand questions related, for example, with the amount of oxygen that we need, how long a corrosion can be sustained in the absence of high oxygen, where anodic and cathodic reactions will happen. You don't need to prescribe that in the model. The model will give you that answer. And this allows us, when we come to predicting corrosion-induced cracking, we can combine these models with those facial fracture models that I showed you before. And then we can use these models to predict not only those accelerated corrosion tests that I showed you at the beginning, but also run simulations over timescales of decades and predict corrosion of reinforced concrete structures under natural charge-conserved corrosion conditions. So we can go from fast tests to real-scale applications. We've also incorporated the role of the electric double layer with a suitable definition of an equivalent circuit model. And I don't have time to discuss this, but this was presented by my PhD student, Maciek. And finally, we have also combined this class of models with hydrogen and betterment models. We're becoming greedy now, and we want to simulate everything, but why not, right? In this way, we can present a generalized model for stress corrosion cracking, where we don't need to make any assumptions on whether damage is anodic dissolution driven or hydrogen driven. We simulate everything that is happening and let the model decide, let the model pick the mechanism. So all the electrochemomechanical machinery that we had before, we now add a second phase field to describe the behavior of cracks. We predict the uptake of hydrogen to the metal by adding to our electrochemistry model the hydrogen evolution and absorption reactions. And we model of transport of hydrogen within the metal and the embrittlement process, the fracture of the metal due to hydrogen. And in this way, we can predict stress corrosion cracking for any choice of environment. And we can see the pitch to crack transition and how changes in corrosion front geometry lead to different electrochemical behavior and hydrogen uptake conditions. And I discussed this more at length in the EUROCORR meeting through a talk that I gave. I was more focused on gaseous environments and more focused on using this kind of mechanistic models to predict under which conditions we can transport hydrogen safely in natural gas pipeline infrastructure. And this is something this is a talk that also gained significant attention, so I decided also to record it and upload it in YouTube. You can find it somewhere in my channel. So let me just finish with a few concluding remarks. The first one is that I feel that this is a very exciting time because the combination of two recent developments, multiphysics and phasing modeling, enables us to fully resolve the physics of corrosion. So we can put forward a framework that does not need big assumptions or fitting parameters. Quite the opposite. It relies only on physical properties that can be independently measured. We don't fit the parameters to predict the experiment. We know the value of the parameters before running the simulation. Another strong point is that this is a very flexible framework that can easily be extended in multiple directions, and it has no computational limitations. You can simulate problems in 2D and 3D with multiple pits interacting, intergranular corrosion, secondary particles, whatever you have in mind. Additionally, we have tried to contribute to this community and try to capture the richness of corrosion by extending the framework in multiple directions. I provided some examples. I'm listing some of them here. But I think what is exciting is that, as I said, corrosion is a complex and rich problem, but we finally have the tools to incorporate the richness and physical complexity into our models. So we don't need to make assumptions. We can solve things from mesoscale first principles, so to say. And I will try to incorporate what we think are interesting physical ingredients, but I'm sure that many of you have other ideas in mind. And also you may want to use these models to answer other questions that we haven't even touched. Corrosion has too many questions to be answered by one group. So the possibilities are immense, and I feel very lucky to work in this exciting field. These are very early days, but I can see this growing already quite significantly and quite quickly. I'm sure that there are many things to polish, but again, this is a very exciting area, and I think that is ready for you guys to jump in. And to facilitate that, we have released openly all our codes. Some of these codes were developed in our in-house codes in C++ or MATLAB. Many others were implemented in commercial finite element packages as COMSOL. So you're welcome to download them from the website, and you can reproduce all the results that I sent you today. And of course, I must thank all my sponsors and thank you all for your kind attention. Thank you.